Then another factor is insulation damage. Like during construction, we place the reinforcement, we put a layer of soil over that, then it will be like a spreading, grading, then with the rolling. In that process, the reinforcement may undergo some damage. So its strength will reduce actually. So again, I have to factor that into design. So again, this insulation damage testing will be done. This actually simulates the actual construction process. So basically, they will take different types of fill material. That means sand, gravel, crushed rock, like that, different types of fill materials. Then simulate the actual construction process. Then they do the rolling. Then that reinforcement is removed. And again, here we have to be very careful actually. We have to do the rolling, but while removing, again, we should not do any damage to that, because like suppose I dig with the JCB, in that process I have damage, it will not be correct actually. So there were again procedures to do the test actually. Then they test two sets of samples. One is in the virgin, like undamaged, that means fresh samples they will test. Then after this insulation damage, again they will test. So this ratio, it gives the reduction. Tensile strength of the virgin product, that means fresh sample, divided by the tensile strength of the damaged product. So this becomes my insulation damage factor. So again, manufacturer give this test reports. Then depending on, I have to look at my site, which type of fill material I am going to use. Then an appropriate reduction factor I have to pick up. Then durability, like our reinforcement is sitting in the soil for 50 years, 100 years time. So it is being attacked by various chemicals, microorganisms. So how much the strength reduces. And fortunately we know like polymers are very chemically very resistant. So again, there are default reduction factors, because or we can go for long-term chemical test. That means I put my sample into acids, alkalis, exposed at various times, again take it out and test. I can find out how much the strength has reduced. But these are like expensive long-term tests. So most of the codes give a default. That means if it is polyester, there are some index properties like molecular weight, carboxylate group. So if this is type of polyester, okay, this temperature, this pH, you can use this reduction factor. Or if I want to be more accurate, I can go for long-term test. Again, the manufacturer gives you these reduction factors. Then another is reduction factor weathering. See, normally polymers, we know they degrade when exposed to the sunlight, basically to the ultraviolet. And this happens only prior to insulation. Once it is within the soil, then there is no exposure to UV. But during actual laying, some exposure may be. See, as long as it is 1 day, 2 day, no problem. But if it is by mistake, if it is exposed for say 6 months, then significant reduction can occur. So normally, if it is covered within a day, then reduction factor can be 1. There is no cause for concern. So third is pull out, like the reinforcement, as I mentioned earlier, the maximum tension is at this point, and basically we have to have adequate anchorage length, or what we call the development length. So if my reinforcement may be very strong, but if adequate length is not there, then it may pull out. So bond failure, tensile failure may not occur, but bond failure may occur. So I have to ensure that it has adequate bond resistance. So again, this very simple calculation, basically bond resistance is through friction. Right? So here actually there is a factor of 2. Basically if you have reinforcement, there is upper face, lower face. So the area into 2 into the length, length will give the area, then the coefficient of friction into what is the vertical stress. So that is my frictional resistance. Then we'll have to ensure adequate factor of safety. So this is simple lumped, like depending on the load factor, resistance factor, then each load combination we have to check actually. So again, if the length is not, remember like initially we had checked for 0.7 times height as the trial length. Then we have done external stability. Then here also, if the required factor safety is not achieved, we have to increase the length. And again, see, most, like suppose it is a geogrid, then if you do actual design, normally the pullout problem happens only here. Like if you look at here the anchorage length is very large, plus the normal stress is also very high. So here, typically if you look at an actual design, the factor safety may be 30, 40 of that order, like that. It will never pull out actually. If at all, it will break in tension only. But the upper 2 or 3 layers, we'll have to check for pullout. Like, because as we come up, the anchorage length is reducing, plus normal stress is also reducing. But of course, our tension also will be less. But still, upper 1 or 2 layers, sometimes the pullout may be a problem. So we'll have to increase the length. Again, there is a coefficient of interaction in pullout. Earlier we have seen sliding actually. So there actually one part of soil was sliding over the reinforcement, internal sliding. Here what, like we have upper part of soil, lower part of soil, and the reinforcement is, we are pulling out like that. So here normally we can conduct a pull-out test. Like we have a box with soil. In the middle part there will be a reinforcement. Then we can apply different normal pressure. Then we pull out the reinforcement and find what is the pull-out load. And again, that is related to the angle of internal friction of the soil with a factor, the coefficient of interaction in pull-out. Again, these factors are given by the manufacturer. So the actual, this is by Emil, they have a pull-out apparatus. We can also conduct field pull-out test. Like this actual, like we put a what we call a dummy layer. In the actual wall also we can do this. We put a slot, we put an extra layer of reinforcement. Of course, like a short length and maybe half a meter width. Because if you put a too long a reinforcement, it may not fail in pull-out, it will break only. So that is not, so when we do a pull-out test, we should have to ensure that failure will be in pull-out actually. So, see, normally with geogrid, pull-out is not a big problem, but if you use strips, then it becomes more critical because the area is less. So sometimes, like if, especially with the steel strips, as I mentioned earlier, there that pull-out factor is very high. So sometimes it's like to ensure that the pull-out test is commonly done at the site. But for geogrid, it's not that critical. Like. Then these three, like internal sliding, adherence, and tension, like we are checking for each layer separately. So this is like a local stability, we call it. Then as the wall as a whole also will have to check sometimes. See, normally what happens in a normal wall with regular geometry, see, once you have analyzed the local stability, like the overall may not be a problem, but sometimes there is a change in geometry, or there are, especially in a bridge abutment, there are heavy loads, then this becomes much more important. So here, like each wedge is taken, then total force in this wedge is compared with the available resistance, like contribution, we add up all the contributions, then analyze the stability. Like actually the BS, they call it internal wedge stability. So normally the FSW ASTO they call like compound stability. Same principle, like instead of like wedges, we take this trial slip circles. So this can be done in typically using slope stability type of approach. So compound in the sense it passes partly through, it's partly internal and partly external. That's why it's called compound failure. Like. Then coming again to the facing and connection stability. Like we have seen the reinforced soil external, internal. Now coming to the facing and connection. Again, various failure mechanisms are there. Suppose it is a facing panel, bending moment, shear force. Then if it is segmental blocks, failure in shear, then sometimes we have connection fixtures, like it may be a steel hooks like that. It can fail in tension, bending, shear. Then this. Now, what is the design load at the connection? As I mentioned earlier, I've shown a slide. The tension along the reinforcement, it varies. So at the connection, what is the value? So actually it varies depending on a lot of factors. But the code, especially the BS code, has given this diagram. The load at the connection, at the top, it is something like 75% of the reinforcement tension. Whereas at the bottom, it is 100% of the reinforcement tension. That means facing with movement capacity at connections. But if it is a stiff face, like sectional block, full height panels, then throughout we have to take 100%. So practically we can say that the connection has to be designed, say practically 100% of the reinforcement tension. Then suppose it is discrete panel, basically we can analyze the bending moment and shear force. So I have assumed this is a discrete panel and there are two reinforcements. So we can take it as a simply supported beam or a slab with overhang. We can analyze the shear force, bending moment diagram. Normally you will find, even if it is a 10 meter or 15 meter high wall, you take the full active earth pressure. If you analyze, you will find the bending moments to be very, very small, because the span is only maximum 0.8 meter, because vertical spacing is restricted to 0.8 meter. And you will find, because I have checked it many times, basically the concrete is what we call an uncracked section. So that means theoretically you don't need any reinforcement, even plain cement concrete will work. So what you provide is a nominal reinforcement for shrinkage, temperature, like that. So the minimum, like as IS 456, like 0.12% of the cross-sectional area, that is enough. Then coming to sectional block facing, this is what is a crest toppling. Like this is the uppermost reinforcement layer. So if there is a large height over this, it will be unstable, like it topples. So here you have to ensure that it doesn't happen. Second is the connection failure. That means the connection between the block and the reinforcement, it could be a frictional connection or a positive connection. So here basically this is from the NCMA, like which is specific to the sectional walls. They give a very detailed procedure how to analyze for crest toppling. That means we have to analyze the stability of this basically as a cantilever wall. Then so ideally what it means is that we'll have to check if we provide reinforcement there like that. And again, when we have a sloping surcharge, you have to be very careful. And sometimes it happened, originally the design was like a horizontal surface. Then sometimes it was revised. They found, okay, my road level has to be higher. So without modifying this design, people have constructed. Then it has collapsed like that. Incidents have happened in practice actually. Then sometimes what happens, then the failure comes to the, like say, okay, the product has failed. Like it's not that. So basically the design was not correct. Then connection strength. So that means at the connection there is a tension which is almost 100% of the reinforcement tension. Then I have to compare with the connection strength. So how do I test that? So here we can see like segmental blocks. This is one block. There is another block and the reinforcement is in between. Then this is actually the section. Then we pull the reinforcement. We can apply the normal force also. That means if it is a wall, like if the reinforcement is say 5 meter below the top of the wall, so that much weight is acting on the reinforcement. So that much normal load I have to put. Then I try to pull out. Then I know what is the connection strength. So this shows the plan arrangement. That means this is the facing blocks and the reinforcement in between. Then there is a pulling arrangement. I just pull. Then basically we have this as the connection capacity is a function of the normal load. This is similar to our direct shear. Like we put a normal load, basically if it is a frictional connection, strength comes from the friction. That means friction between blocks, concrete, or sometimes what happens in the hollow blocks there is aggregate. So that will be additional. So like here. So like this type of, this is actual test reports like. And again, like each type of reinforcement, each type of block, it will have a different curve like that. So each product has to be tested. Like suppose I have a particular block, I cannot use this with another type of block. Everything has to be similarly, like same company's product, like suppose 40 kilonewton, 60 kilonewton, each will have a different curve actually. Like each product has to be tested. Then finally in the methodology, basically we like actual, it will be a curve, something like that. Then we like linearize into segments like that. So then we can put a formula into that. So if it is in this zone, I take this formula. If it is in this zone, I take this formula. Like so, there will be an equivalent apparent. Like we don't want to call it a cohesion. Like it is a intercept actually. Like that. It's not. It doesn't mean there is a cohesion there, but basically it's come from the curvature like that. So basically we are doing curve fitting like some parameter. So this we can put in the calculation method. So in a wall at each level, I know what is my normal load. So from this, I can pick up what is the connection capacity. That I compare with the connection load, ensure a factor of safety. Then, so now next is serviceability. Like we have ensured stability. Next is serviceability. So for a reinforced soil wall, there are two. Like one is settlement, vertical settlement. Another is lateral deformation. How much the wall deforms laterally. Again, there is a see normally codes specify, again it depends related, as I mentioned earlier, the allowable settlement depends on which type of facing I am using. Some facing can tolerate more settlement, whereas some less like that. So these are specified. So basically, and again, normally most codes they specify the tolerable, that means what you call the angular distortion. Like 1 in 100 means over a distance of 100 meters, there can be a differential settlement of 1 meter. That is allowable like that. Then again, post-construction creep strains, one for walls, that is walls with a normal retaining function. Then 0.5% for bridge abutments, because bridge abutments will have to be more conservative. Now, how to construct the post-construction strain? Again, we have this what are known as isochronous curves. So this gives the stress as a percentage of ultimate tensile strength from 0 to 100%. This gives percentage strain. Then this gives different time like that. See now this from the creep testing we have this data. See now my limit is actually on the post-construction strain. Some strain may happen during construction, so that is fine like that. So after I have completed the wall, how much, after that how much? So the code limits actually that 1% post-construction strain. So basically here, okay, let us say like my construction takes about 1000 hours. So I come to this line. So see normally if I apply all the reduction factors, our actual tension on the reinforcement will be something like between 30 to 35% of the ultimate tensile strength. So I have put this line, I come here. So this is my, and what is my design life? Let us say like this is 114 years. So this will be my post-construction strain. So I have to ensure that this is within the permissible limit. Then only our IRC, they have put, see normally foundations, when we design footings, there is a limit on the total settlement. Because actually the important is the differential settlement, but calculating differential settlement is a bit difficult. If we put a total settlement, that makes the life of designer much more simpler. So like footings 50 mm, raft 100 mm, we have like that. So our IRC has done something like they have put the criteria, post-construction settlement of the funding soil should not exceed 100 mm for discrete panels and blocks like that. Whereas almost all the other codes, they have not put a limit on the total settlement. See now, like, see, one aspect I did not mention was which pressure theory to use actually. Like, so here I've given a comparison like the BS, like it doesn't say like Coulomb or Rankine, but in that they have put a diagram. This is delta is the angle of wall friction. For tie-back wedge method, it should be 0, which indirectly says it implies Rankine theory. Whereas internal stability, it doesn't say anything at all. Whereas if it is coherent gravity, then Coulomb implied. Whereas if French code, they say this earth pressure theories, because there are French people. Whereas internal stability, Rankine. Similarly, FHWA, if the battery is less than 10 degrees, that means the inclination from the vertical is less than 10 degrees, we go with Rankine. If it is more, we can go with Coulomb. Whereas NCMA, it's Coulomb only. So we know, like, if you use Coulomb theory, normally the pressure will be less. That means our design will be a bit more economical. Then these are the other important aspects, like drainage is very important, like scout protection. Then facing from vehicle impact, because these panels or blocks are very slender structures. So like in a highway, we don't want a heavy truck to come and hit actually. So sometimes they have a curve, like these are important. Then sometimes, like we have constructed the wall, then we don't want somebody to dig a trench at the top and cut the reinforcement. So these kind of things we have to anticipate and provide for the design. Then like if we compare the RCC retaining walls with the reinforced soil walls, like one important difference is, like if you look at the concrete wall, these are simple materials actually. Like steel, the properties are very simple. Like we get the tensile strength, modulus we get. Similarly, in the case of concrete, see all the properties from a cube test. Like we do a cube test. Once we get the compressive strength, then bond strength, shear strength, everything comes from that actually. And we can do it at a site. So any cement, I can always do a cube test, no problem like that. But whereas here, the design is based on the long-term design strength. That means creep, durability, insulation damage, these are all come from very complicated tests actually, time consuming as well as very expensive. So each project I cannot do that actually. So always, similarly interface friction, connection strength. So suppose I'm a designer, I have a project. So now if I say, no, I want to do all this test, that's not possible actually. So these are all very time consuming, expensive tests. So we have to take this data from the manufacturer. So we have to rely on the data. So we have to verify. So for that also, there are third-party testing. We have to look at the laboratory which has given. Then there are certifications. That's very important. Second is, in the case of conventional wall, the soil is only a retained material. Like if I make a RCC wall, the soil is poor quality. It is not compacted. At the most, the earth pressure will be more. Factor safety reduces, but the wall may not collapse. But in the case of reinforced soil, the soil is a structural element. So I have to be much more careful with the soils. So I cannot just look at the reinforcement. I have to equal importance to the soil. Then to conclusions, it's a wonderful technology, like proven, everything is there. Like we have everything in the country. Like today, like the products are manufactured, like geogrids. There are 3 companies. Polymeric strips are being manufactured. Now we have a code also. Everything is there. And it's a very versatile, proven system with a lot of benefits like cost, construction, performance, everything is good. But only like proper material characterization, like reinforcement, facing, soil, everything we have to do with care, then proper design and construction. Okay, with that I conclude. Thank you.